Physics 9702, Elementary Lattice Dynamics and High Mark Exam Strategy. If you're studying for this exam right now, there's this silent misconception that's probably bleeding your high-level marks dry. Seriously. The way you're picturing the microscopic structure of materials, it might be working completely against you the second you sit down to write your answer.
Are atoms in a solid frozen still? You see, most students unconsciously picture a highly ordered crystal as this completely static thing, kind of like a rigid 3D grid of marbles glued perfectly in place. Well, I hate to break it to you, but that's a total myth. And if you write your exam answers based on this frozen picture, it's going to actively cost you grade boundaries, especially, and I mean especially, when you get asked to explain thermal properties, heat capacity, or energy transfer. The exam board absolutely knows this is a common trap, and they literally design questions just to expose it. So, reality check. Atoms continuously vibrate about their equilibrium positions. Even in a highly ordered, super rigid crystal, they are never ever truly frozen. And once we actually accept that solids contain this constant, relentless motion, well, the door just swings wide open. We transition away from just blindly memorizing abstract formulas, and we move towards a much deeper, examiner-approved explanation of heat, thermal energy, and wave-like behavior in matter. This whole topic, it's not just a laundry list of equations. It's a story of collective motion. And understanding that story is your ticket to those top-tier marks. Let's break down exactly how this builds on a microscopic level. Just imagine sketching atoms on a blackboard, and they're joined conceptually by these little elastic links. Now, what happens when just one single atomic position is disturbed? Well, that gives us step 1, local displacement. But because of those elastic restoring links acting almost like little springs, that one moving atom is going to yank on its neighbors. And that brings us to step 2, elastic coupling. So we don't just have isolated random shaking going on here. The disturbance actually travels right through the material, which creates step 3, wave propagation. The end result is this beautifully organized set of vibrational modes spanning across the entire lattice. And that, my friends, leads to the ultimate breakthrough, step 4, quantized energy. By walking through displacement, to coupling, to propagation, and finally to energy storage, we've literally just turned a highly abstract idea into an intelligible, step-by-step physical process that you can confidently write down in an exam. Now, this organized wave motion introduces a critical vocabulary word that you absolutely must have in your toolkit, the phonon. A phonon is a quantized mode of lattice vibration. You really need to think of it as the ultimate bridge. It's exactly how physicists connect microscopic atomic motion to measurable macroscopic thermal behavior. Look, a phonon isn't a tangible physical particle like a proton or an electron, right? It's a way of describing and quantifying those organized waves of vibration we just talked about. Getting this definition perfectly locked in your head, it's completely non-negotiable for Cambridge exams. So, the million-dollar question. How do we actually revise this massive concept effectively? Well, you do it by mastering these 4 anchor prompts: definition, microscopic cause, macroscopic consequence, and real application. If you can speak through these 4 prompts in order, you can usually reconstruct a highly robust exam answer, even if the examiner phrases the question completely differently from what's in your class notes. Now, in just a minute, I'm going to show you the exact examiner clue that changes your answer completely. It's a trap that catches literally thousands of candidates. But first, we really need to understand how to apply these anchor prompts to macroscopic consequences. And that brings us to a major consequence you will inevitably face on past papers. Why is heat capacity not just some arbitrary graph? Well, it's because a material responds differently to heating, based directly on how its allowed vibrational modes become populated. If the lattice can store energy in, say, many allowed quantized ways, the macroscopic heat capacity naturally shifts. This creates a really strong, undeniable bridge between our microscopic crystal model and a macroscopic thermodynamic quantity. So when you're asked to analyze a heat capacity graph in an exam, teaching yourself to look beyond just the X and Y axes is absolutely vital. Don't just read what the graph shows. Ask yourself, what underlying lattice behavior must be happening to actually cause that curve? Let's put that real application prompt into practice. The real-world value of lattice dynamics is massive, and examiners absolutely love it when you can provide some technological context. Just think about thermal management in electronics, for example. Preventing your computer's CPU from literally melting depends entirely on how vibrational energy moves through solids. Materials used for power systems, spacecraft, and precision sensors are all limited by how they store and transport this energy. Even acoustic crystals and thermal barrier coatings rely on the exact same underlying physics. A student who can confidently relate abstract lattice dynamics to an overheating microchip or a super temperature-sensitive precision device, that's a student who's going to write a deeply convincing top-band exam answer.
All right, let's actually put this exam technique to the test right now. Compare the flawed answer with the top band answer. The flawed one says, heat makes phonons vibrate. Now sure, it sounds kind of scientific to a novice, but it's completely backwards. It totally lacks cause and effect reasoning. Now look at the highly structured answer. Thermal energy is stored in quantized lattice vibrations. Do you see the difference there? The elite answer doesn't talk about heat doing some vague action to a phonon. Instead, it precisely connects the concept of thermal energy directly to the specific mechanism of quantized lattice vibrations.
Which brings us to that critical examiner-style correction I promised you earlier. Here's the ultimate examiner clue for this entire topic. Never mention phonons without explaining exactly what is being quantized. Seriously, a frequent and honestly devastating mistake is to just drop the word phonon into an answer to sound smart without actually explaining that it represents quantized lattice vibrations. Talking about heat in this vague, hand-wavy way without explicitly linking it to these internal vibrational states, it's going to cost you crucial grade boundaries. The mark scheme is practically hunting for that explicit connection. If you write the word phonon, your very next thought must automatically be quantized vibration.
Okay, so you now have the conceptual framework. You know how to take atomic motion, trace it through elastic coupling into wave propagation, define the phonon, and connect the whole shebang to macroscopic thermal solids. But knowing this strategy is really only half the battle. You need to know how to actually apply this when your physics exam is imminent and the pressure is at its absolute peak. Organizing this exact level of mark scheme thinking across the entire syllabus with only a week left, that is exactly what separates the top-tier candidates from the rest of the pack. Replacing last-minute panic cramming with a solid, high-retention system is your next mandatory step to secure your grade. To get your hands on that exact system, check out our Physics 9702 Last 7 Days Revision Map Explainer right now. And make sure to subscribe to our YouTube channel, Ace the Exams, at acexams_IGCSE for more. But hey, before you go, think about this. The next time you pick up a piece of solid metal, ask yourself, how much of its heat is really just a silent, microscopic symphony of quantum waves? I'll see you in the next explainer.